Here we go. So we're going to talk about independent and dependent events today. So what I'm going to be able to do is identify, if I give you some situation, whether or not certain events are dependent or independent. So it's going to be two or more. So does the outcome of the second thing or the third thing or whatever, does it depend on what happened with the first thing that happened? Okay. And independent is they totally, one doesn't matter with the other. So dependent so the outcome of, we'll just say second event, we'll mostly just talk about two, depends on the outcome of the first. So something happened in that first event that's going to change how the second event works. That's dependent. Okay? So this is probably self-explanatory, but an event doesn't depend on the first. Yeah. It can be pretty easy. It can be kind of challenging, depending on what I'm talking about. So, some situations, and you tell me whether you think those events are independent or dependent of each other. Try that again. Independent. I don't know, I guess maybe. Okay, so here are two events. My first event is I'm going to flip this coin. My second event is I'm going to roll this die. Are those two events independent or dependent? Independent. Whatever I get from this coin flip is not going to affect what happens when I roll this die, right? Okay, so those are independent events. I got tails in it too. Another situation. I got a deck of cards. Oh, that one looks ugly. These are nicer ones. Okay, so I'm going to take a card at random out of the deck. That's my first event. Okay. I'm going to put it back in the deck, and I'm going to pull another card at random out of the deck. Are those two events dependent or independent? Shh. Hold on. So, I took the first card out. I put it back. So now I have... You have to assume everything's random when I take out a card, okay? So I take this card, okay? Then I put it back in the deck. So now I have a full deck of cards again. And then I pull out another card out of that full deck. Does the pull of this second card depend on what card I pulled out the first time? No. Because I put it back in, and presumably it's all random again. So I still have a full deck of cards. So each time I'm pulling a card out of a full deck of cards, right? It would be the same as if I took a card out of this deck and then a card out of that deck. Two separate decks, totally independent, right? They're not even the same deck of cards then. It's mathematically, probability, whatever. It's the same as doing that. So those are independent. If I do, okay, I'm going to take a card out of this deck. I'm going to put it on the table. And now I'm going to go back and take another card out of this deck. That's dependent, right? Because the cards that are in this deck are now affected by what card I happened to take out the first time, right? So now it's dependent on whatever this happened to be, right? Okay, so that's the difference with that. Let's see if I can come up with some other ones for you. What if, okay, my first event is I'm going to pick a student at random or some that I want. All right, and then I'm going to pick another student out of this class. Are those two events independent or dependent? Dependent, because I'm not ready for a committee and then sit them back down in the room and then pick again, right? It's kind of like the card situation, right? I'm already out of the deck, and I have a smaller deck to choose from now when I pick that second person, okay? So those are dependent events. Dice, and I'm going to roll it 2 times. Independent or dependent? Independent, because the second roll does not matter. It doesn't. The second roll is not affected by what I got by the first roll, right? Okay. So that's the idea, being able to determine whether events are independent or dependent. Okay. All right. So now is identify that when you're ready. Oh, you are. Oh, good. So how do we calculate probabilities of independent and dependent events? Well, you guys were kind of doing this a little bit already yesterday. The independent events you were. Independent events are the easy ones. Independent. Got it. Okay, so that 2 things are going to happen, right? When I'm talking independent and dependent events, I've got 2 events. So it's going to be the A and B. So if A and B are my 2 events, and we have determined that they're independent of each other, the probability of both of those 2 things happening is the probability of A multiplied by the probability of B. So, if I go back to the first situation with my coin and my die.
Please excuse the interruption. We have a few announcements. First hour E10 is continuing to sell Team Winchester Baby Egg t-shirts. T-shirts are now available at a reduced price of $10 each.
What?
Pick up your t-shirts soon because the supplies are limited. The dodgeball tournament is also this coming weekend. There is still spots for teams to sign up, so sign up today. If you have any questions, please contact Kate Backheim, Amber K. Wood, Holly Van Valkenburg, or Brandon Ryan. Students interested in participating in an interscholastic bass fishing tournament, please see Mr. Veld for more details. Thank you.
So let's look at this. We've determined that flipping a coin and rolling a die are independent events, right? One does not affect the other one. Okay, so you roll a die, you flip a coin. What is the probability of a 3 and heads? Now, before, what you guys would do was you would list out the entire sample space. Okay, I can get a heads with a 1, or a heads with a 2, or a heads with a 3, or a heads with a 4, a heads with a 5, a heads with a 6, or a tails with a 1, a tails with a 2, a tails with a 3, a tails with a 4, a tails with a 5, or a tails with a 6. And then figure out how many of those combinations work. Or you could ask yourself, if rolling the die is event A, what's the probability of a 3? 1/6. If this is event B, what's the probability of a heads? 1/2. So the probability is 1/12. Yes. Okay, so the probability of a 3 was 1/6. So the probability of 3 and heads is equal to 1/6 times 1/2. It's 1/12. That's doing a problem with independent events. Just figure out each situation on its own, multiply the two probabilities together. Okay? All right. So, independent and how we do those. And then I'm going to give you a bunch of problems in different situations, and you have to determine is it independent or dependent, and then do it either way, depending on what you have. Depending. Nobody caught that. All right, so dependent events. So in this case, the probability of A and B, it's actually very similar. It's the probability of A multiplied by the probability of B given A. That's how that's said. Now, it's easier to understand in practice. So if I give you an example problem, it'll make a little bit more sense. But so the probability of A, that's still the same. So the first event, whatever it is, you just, what's the probability that happens? And then the second probability you multiply it by is a new probability that is based on what has already occurred. Give you an easy example of this. The deck of cards, okay? Let's say the probability of if I draw a card, don't put it back in, and then draw another card, that both those two cards are queens. Okay? Now, those are dependent events, right? If I don't put the card back in, I got left. They're dependent. So how do you do that? Okay, so let's just jot that problem down. So what is, you pull two cards from the deck. What is the probability both are queens? Okay, so the first we can do just like we've been doing. Is there in a deck of cards? 4 out of a total of 52. Okay. And you can reduce that, what is that, 1/13, right? Now, what is the probability of a queen given that you've just pulled a queen? You got it. 3 out of 51. Does that make sense? If I pull the queen out of the deck, how many do I have left? 3. How many total cards do I have left? 51, right? So it's going to be 1/13 times 3 over 51. Okay? It's a very small probability. So the queen is going to be 1/13 times 3 out of 51. So that's 3 out of 13 times 51. 663.
What? Can you simplify 3 over 51?
We can simplify to 3 out of 663. That'd be 1 out of 221. So the pulling out 2 queens in a row randomly out of a deck is 1 out of 221. It's not real good odds.
I bet I could do it. Give me the card.
It would take you around 221 tries to do it, but no. Does that make sense? Changed because of the outcome of the first one? You have to think about how do I still have? and then kind of from there. Okay. So let's try questions here. See if you can identify. Is it independent or dependent? Can you then calculate the probability correctly based on what you got? Okay. All right. So. Oh, you spin it twice. All right, so you spin a spinner with 7 spaces, numbered 1 through 7, twice. What is the probability that the first spin is an even number and the second spin is an odd number? Shh. Just do it. Oh, sorry. I want you to try it on your own. I'll freeze it, write the answer, and then see if you guys come up with the same thing as me. And if you would, write this as a percent when you're done. All right, everybody got an answer? About 24.5%. Independent or dependent events? Independent. You're doing a spinner, right? So whatever you spun the first time, it's not going to affect what you get the second time you spin it, right? So you just do the even spaces. There's 3 out of 7 of them are even. Odd spaces, 4 out of the 7 of them are odd. Multiply those 2 fractions together, you're done. Good. Okay. I don't necessarily. Whoops. No. No, we're going to do a little bit of conditional probability to finish up, but it's not much. This $100 bills, 10 $1 bills, and 3 $20 bills.
Yeah, but you know, you can't go from the smallest to the biggest.
Yeah?
Yeah.
Oh, good. All right. Try that one. A purse has $500 bills, 10 $1 bills, and 3 $20 bills. You pull out 2. What's the probability that you get 2 hundreds? Yep. Right. What's event A and what's event B? Event A is the first pull. Event B is the second pull. Because you're pulling out 2 $100 bills. So don't think about events as the things that you have. Events are events. They're actions that happen. So the 2 actions were you pulled out 1 bill and then you pulled out the second. So think about those 2. Are those independent or dependent things? And if so, then what do you do? Yeah, that'd be great. All right, everybody got something for this one? Yeah. All right, let's see what we got here. 0.5% on that one. Are these independent or dependent? Dependent, right? Because your number of bills in the purse, as soon as you take the first one out, has decreased by. And if the first $100 bill, which we wanted, you're going to have one less $100 bill in there as well. So 5 over 18, because there's 18 total bills in there, multiplied by 4 over 17 is 20 over 306, which is 6.5%. Okay? So, feeling okay with this stuff? Independent, dependent? Okay. Additional probability.
What happened to the short lesson you promised? You didn't promise us.
I really didn't, but like half a page. I'm going to just do one example, we're done.
Oh my God! Yeah, they're gonna give you your seat right now. Break your seat. No, it's a choice. Shut up.
The little formula we had for the dependent stuff, right?
Yeah.
Okay. The one right there with the P of A given B, That's called a conditional probability. It has a condition on it. The probability of A with the condition that this other thing already happened. Right? That's what that is. So we have a formula for this if we just do like a little algebra with these probabilities and move them around. So the conditional probability, A, given that B has already happened,
So instead of B over A, it's A.
like I said, it's just a little algebra. I'm just doing a little dividing, moving that one probability over to the other side. It's not anything crazy. It just moved it. Okay, so we have a formula then for the conditional little piece of that, if we would like. The probability of A and B, if we know what that is, divided by the probability of just the first event happening. So depending on how the information is given to you, you might need to do this if we're searching for that conditional probability. And I'm going to steal an example out of your textbook because I think they do a pretty decent job with this. Talking about school lunches. What? All right. So that's example 7 if you'd like to read along. So at a school, 60% of students buy lunch. Now, I don't know if it's that high here. Do you think? 60%?
It's about 75.
I don't know. Maybe a little higher. Yeah. Anyway. So only 10%. So only 10% who already bought a lunch. Okay. So what is the problem? 10% of students buy lunch and I wrote that wrong. So, well, then just start over. Sorry. I guess you could do that. Way too much effort. Okay, here's how it's supposed to go. Sorry, I had the two last sentences switched in my head. Only 10 buy dessert and a lunch. Period. Okay? So we want to know what is the student who buys lunch also buys a dessert? Okay. All right. So there are two probabilities in this question. Okay. 60% of students buy school lunch, a dessert and a lunch. Those are the two probabilities. Now we need to figure out what is event A and what is event B, and then how do those probabilities relate to that? Okay. Shh, guys, just hang with me. We only got like 5 more minutes of this, and I'm done. So what is event A and what is event B? Mm-hmm. That's a colon.
Oh. I didn't do a very good job. I thought it was, I understood what you were. Yeah,
Event A is they buy lunch. Event B is they buy dessert. So, what is the price of A and B? 0.1, right? 10% of students buy a lunch and a dessert, A and B. 0.1. A is what? 0.6. So I want to know, what is the price who buys a dessert? Do you see the condition on that? I want somebody who bought a dessert, but it's only those people that bought the dessert that bought the lunch first. So buying a dessert given that the lunch already happened. That's the condition, okay? So A given B, that's what I'm looking for, right? Okay, so I can use this little formula I came up with up here to find my answer then. Yeah. So it'd be 0.1 divided by 0.6, right? Okay, so what's that? Well, 1/6. We can all do that math, I think. And 1/6 is about 16.7%. That's it. Okay. All right. So, independent, dependent, conditional. You got it.